Hi, everybody. It's Professor Mitchell. We're starting a new chapter today, Chapter 9 on Inequalities and Absolute Value. So the first section is 9.1 on compound inequalities. And in this section, we're going to find the intersection of two sets, solve compound inequalities containing and then find the union of two sets and solve compound inequalities containing or. And the SLO for this section is to solve linear and nonlinear inequalities. All right. And in this case, I guess they would be linear. All right. Kind of a little bit of a gray area. Okay. So compound inequalities and the intersection of two sets. Two inequalities joined by the words and or are called compound inequalities. For example, x plus 3 is less than 8 and x is greater than 2. So that is one inequality joined by the word and. So what it's saying is that any solution has to make both of those inequalities true. And another example is 2x minus 3 is greater than or equal to 4, or 5x plus 6 is less than -7. A value x will be a solution to this compound inequality if it makes either one of those inequalities true or both. So in mathematics, the word or is almost always an inclusive or, which means one or the other or both. It's a little different than how we use it in everyday English. All right, so we'll start with the intersection of two sets. The intersection of two sets A and B is the set of all elements common to both A and B. In other words, the set of elements that are in A and B. All right. The intersection of A and B is denoted like this, with this kind of upside down U symbol. And then the union of two sets A and B is the set of all elements that belong to either of the sets or both. In other words, the set of elements that are in A or B. The union of A and B is denoted like this, with a right side up U. All right, so just remember U for union. What you're looking at here, these are called Venn diagrams. They show the relationship between two sets. So that if the circle on the left is A and the circle on the right is B, the shaded red area is the intersection of A and B. And in this picture over here on the right, the shaded area is the union of A and B. So everything that belongs to A or B or both. All right, so for our first example, consider these four sets. A is the set of all x, such that x is an even integer. This is called set builder notation. So it's a way of writing the set of even integers. B is the set of all x, such that x is an odd integer. And then the set C just contains the four elements 2, 3, 4, and 5. And the set D contains the four elements 4, 5, 6, and 7. So in this example, we're going to list the elements of each of these sets. Did I do? Oh, okay. I was thinking of a different problem. All right. So I'm going to go over to the tablet. And here we go. Okay, so we're starting with C intersect D. So these are the elements that C and D have in common. So just look for the numbers that belong to both sets. And you can see that the numbers that belong to both sets are the numbers 4 and 5. So that would be C intersect D. C union D contains all numbers that belong to either C or D or both. So that would be all of the numbers that you see listed in either set. 2, 3, 4, 5, 6, 7. Notice I'm only writing the numbers 4 and 5 one time. When we list the elements of a set, we never repeat. And also the order that you list the elements of a set does not matter. All right, so I don't have to list them in that order. All right, when we're talking about numbers, I do tend to list them in numerical order, but you don't have to. Okay. Next, we have B intersect D. So B is the set of odd integers. Remember, integers are numbers like -3, -2, -1, 0, 1, 2, 3, et cetera, et cetera, et cetera. Okay, that's the set of all integers. B is the set of odd integers. So that would be like -3, -1, 1, 3, et cetera, et cetera. We're finding the intersection of that set with set D. Okay, so just look for the numbers in set D that are odd. All of the numbers in set D are integers, but only 2 of them are odd integers, right? So that would be 5 and 7. And that would be my answer. B intersect D is 5 and 7. Which brings us to B union D. So this set is going to be a little tricky to write. So we're looking for everything that is either an odd integer or one of the numbers 4, 5, 6, or 7. Okay. So maybe it would be helpful. I don't have a whole lot of room on here, but maybe it would be helpful to draw a picture of this one. Okay, so over here, I'm drawing a Venn diagram. So over here is B. Over here is D. So let's start with D because it only has 4 elements. The numbers 5 and 7 are odd integers, so they go in the overlapping part. The numbers 4 and 6 go over here. And then there are a whole bunch of other numbers in this area over here. All right, anything that is an odd integer other than 5 or 7 needs to go over there. So -3 would go there, -1 would go there, 1, 3, 9, 11, and an infinite amount of other numbers. All right. So the union of B and D has to include all of these numbers. Okay. This is going to be an infinite set. All right. So I think the easiest way to write this answer will be to use set builder notation. So if I start by saying the set of all x such that x is an odd integer, that's going to take care of everything in here and also these two. So the only 2 numbers that I have to add in there that are not already there are 4 and 6. So one way you can do that is to continue the set of all x such that x is an odd integer, or x equals 4 or x equals 6. So if you are any one of those things, either an odd integer or the number 4 or the number 6, you get into the union of these 2 sets. All right, that brings us to letter E. We're looking for A intersect B. So what does the set, or I should say, what do the sets of even integers and odd integers have in common? In other words, which integers are both even and odd? And if you're kind of thinking that that sounds like a weird question, well, you're right, because there are no integers that are both even and odd. All integers are one or the other of those things, but none of them are both. So these 2 sets actually have nothing in common, which means that their intersection is what's called the empty set, which is written like this. Back in chapter 2, we sometimes use that symbol to mean no solution. All right, so that brings us to letter F, which is the union of A and B. Remember, A is the set of even integers. B is the set of odd integers. So the union of A and B would be everything that is either an even integer or an odd integer, which is just the set of all integers. All right, so I don't have a whole lot of room to write this answer, but you can also write that using set builder notation. It would be the set of all x such that x is an integer. All right, back to the presentation. Okay, so in this example, we're going to be solving compound inequalities and writing the solutions in interval notation. Remember, we talked about interval notation back in chapter 3. So we have quite a few examples here, and I have these all on the tablet. So let's go over to the tablet and work through these examples. Starting with letter A, which is the compound inequality x plus 2 is greater than or equal to 3 and 5x minus 1 is greater than or equal to 9. So remember, any solution to this compound inequality has to make both of those inequalities true. So what I'm going to do is solve each of these simple inequalities separately. So if x plus 2 is greater than or equal to 3, that means x is greater than or equal to 1. And if 5x minus 1 is greater than or equal to 9, that means that 5x is greater than or equal to 10, which means x is greater than or equal to 2. So we are looking for all those values of x that are both greater than or equal to 1 and greater than or equal to 2. So what I find very helpful to figure out exactly which values of x those are is to graph both of those inequalities on a number line. So here is x is greater than or equal to 1. So there's 0, 1, 2. Okay, so remember back in, I think I said chapter 3, I meant chapter 2. The graph of this inequality looked like this. You have a bracket at the 1, and then we're coloring everything to the right of 1. And then we do the same thing for x is greater than or equal to 2. 0, 1, 2. All right, and now I need to look at what values of x do those two graphs have in common. This is what you'll do anytime you're doing an AND problem. In other words, just what is the area where they overlap, which would be this area here, the part that's colored in both graphs. All right, which is the set of all x that are greater than or equal to 2. And in interval notation, that is written like this, bracket 2, comma, infinity, with a parenthesis. All right, so let's do another one. And as usual, I encourage you at any time to pause the video, try the problem, and then come back and compare notes. All right, so again, I'm going to solve these two simple inequalities separately. I'm going to start by adding 1 to both sides of this one, which gives me 2x is greater than 4. Dividing both sides by 2, I get x is greater than 2. And at the same time, the opposite of x has to be greater than 2. So with this one, you want to be careful. We'll divide both sides by -1. And because I'm dividing by a negative, that reverses the inequality symbol. All right, so we're looking for all those x's that are both greater than 2 and less than -2. So again, I'm going to draw a couple of graphs. Let's go -2, -1, 0, 1, 2. So the graph of x is greater than 2 will be a parenthesis at 2, and then everything to the right of 2. The graph of x is less than -2 will be a parenthesis at -2, and then everything to the left of 2. All right, so now I look at these two graphs and I see where do they overlap, which values of x are colored in both times. And the answer is none. There is no overlap between these two graphs, which means this compound inequality, 2x minus 1 is greater than 3 and opposite x is greater than 2, has no solution. And again, the way that you write no solution is with the empty set symbol. All right, next example. -7x is less than or equal -21, and x minus 20 is less than or equal to -15. Once again, we solve each simple inequality separately, dividing both sides by -7. So this is another one where I have to switch the inequality symbol. I get x is greater than or equal to 3. And at the same time, adding 20 to both sides gives me x is less than or equal to 5. All right, so let's draw a couple of graphs. And this time I'll go 2, 3, 4, 5, 6 maybe. Doesn't really matter too much which numbers you plot on your number line. Definitely at least include the number that's the endpoint. All right, so x is greater than or equal 3. It look like this. And then 2, 3, 4, 5, 6. X is less than or equal to 5. It would look like this. All right, so where do those two sets overlap? Well, I think you can see where they overlap. They overlap everywhere between 3 and 5, including 3 and including 5. The numbers 3 and 5 are included in both of those sets. So the intersection would be all real numbers between 3 and 5 inclusive. All right, so in interval notation, that set is bracket 3, comma 5, bracket. All real numbers between 3 and 5 inclusive. Make both of those simple inequalities true. All right, this is an example of an AND problem, and I believe we did some of these back in section 2.8. This is shorthand notation for -1/4 is less than 6 minus x over 12, and 6 minus x over 12 is less than -1/6. So as you saw back in 2.8, we can work with all three parts of this inequality at the same time. And because we have fractions, I would start by multiplying all three parts of the inequality by the LCD, which is 12. So let me start by rewriting this inequality. -1/4 is less than 6 minus x over 12 is less than -1/6. Okay, so now I'm going to multiply all three parts by 12. Let's start in the middle. In the middle, the 12s completely cancel and just leave 6 minus x. On the left side, 4 goes into 12 3 times. 3 times -1 is -3. And on the right side, 6 goes into 12 2 times. -1 times 2 is -2. All right, so now I'm going to subtract 6 from all 3 parts, which will give me -9 is less than opposite x, that minus is still there, is less than -8. And finally, because I'm not interested in opposite x, I'm interested in x, I am going to divide all 3 parts of this by -1. Now, what that's going to do is, of course, it's going to change this to a 9. It's going to change this to an 8. It's going to change this to an x. But because I divided by a negative, that's going to reverse the inequality symbols. So what you have to understand about this, 9 is greater than x is greater than 8. This is kind of like saying John is taller than Bob and Bob is taller than Mary. That is exactly the same thing as saying Mary is shorter than Bob and Bob is shorter than, who did I say, John? Okay, all right. And we usually do write these double inequalities with less than signs. It's kind of not standard to write them with greater than signs. And also, when you write the interval notation, you have to put the smaller number on the left side. So this will transition better to interval notation. The interval notation for that set is parenthesis 8, 9, parenthesis. All right, so now we switch over to our OR problems, starting with -5x is less than or equal to 10, or 3x minus 5 is greater than or equal to 1. Any value of x that makes either one of these inequalities true or both will be in the solution set of the compound inequality. So again, I'm going to solve each simple inequality separately. Divide both sides of this one by -5. That gives me x is greater than or equal to -2. And adding 5 to both sides of this one gives me 3x is greater than or equal to 6. Dividing both sides by 3 gives me x is greater than or equal to 2. So we are looking for those values of x that are either greater than or equal to -2 or greater than or equal to 2. So I also recommend drawing graphs to help figure these out. So I'm going to go -2, -1, 0, 1, 2. And I'm going to start with a graph of x is greater than or equal -2. We're going to put a bracket here and color everything to the right. And then x is greater than or equal to will be everything to the right of 2. All right, now remember we are doing an OR problem this time. So don't, be very, very careful. Understand when you're doing an AND problem, understand when you're doing an OR problem, because the answers will almost always be different depending on whether it's AND or OR. This time we're looking for all values of x that are represented in either one of those graphs. All right. So any value of x that got colored even one time will make it into the solution set of this compound inequality. This time we're talking about all of these values of x. Everything that is greater than or equal to -2. So in interval notation, there it is. That would be bracket -2, comma, infinity. And remember, the infinity symbols always get a parenthesis. Okay. Next example. X plus 9 is less than 0, or 4x is greater than -12. So again, solve the simple inequalities separately. So this one gives you x is less than -9. This one gives you x is greater than -3. So we're looking for all values of x that are either less than -9 or greater than -3. All right, now there's a bit of a gap between -9 and -3. Oh, so you know what I'm going to do? I'm going to cheat here a little bit. Nobody said that you have to plot all the integers between -9 and -3. You can just go -9 is here, -3 is here. All right. Just put them in the same place on both number lines. X is less than -9 would be everything to the left of -9. X is greater than -3 would be everything to the right of -3. All right, now we saw a couple of graphs like this earlier. I think it might have been in part B, but that was when it said and. All right, and in that case, the solution set was no solution. It was the empty set because there was no overlap between those two sets, but this is an or problem. So we're interested in everything that is in either one of those sets. So I'm actually going to draw a picture of what the union of these two sets looks like. I don't think we've ever maybe seen this situation before, but it comes up frequently in all of your higher math classes. It comes up in pre-calc, calculus, comes up everywhere. The union of these two sets would be all values of x that are less than -9, and would also include all values of x that are greater than or equal, greater than -3, not or equal to. Okay. So this is not an interval. This is what we call the union of two intervals. And the way that you write this using interval notation is as follows. You write the interval notation for x is less than -9, which is -∞, -9. And you write the interval notation for x is greater than -3, which is -3, infinity. And you connect them with a union sign. So that is what your answer is going to look like. And when you're asked for the answer using interval notation, that's what you're going to write. So you have to use the union symbol. All right, finally, the last example, letter G. 5 times x minus 1 is greater than or equal -5, or 5 plus x is less than or equal to 11. All right, so I am going to distribute the 5 here. There's another way to do it, but I'll stick with what we've talked about before. That gives me 5x minus 5 is greater than or equal to -5. I'm going to add 5 to both sides, which gives me 5x is greater than or equal to 0. And then finally, x is greater than or equal to 0. Okay, so x is either greater than or equal to 0, or this one's a lot easier, right? If I subtract 5 from both sides, I get x is less than or equal to 6. So now let's look at what those graphs look like. And I'll do the same thing I did before. I'll just plot those two numbers. So here's x is greater than or equal to 0. Here's x is less than or equal to 6. All right, so x is greater than or equal to 0 would be a bracket at 0, and then color everything to the right. X is less than or equal to 6 would be a bracket at 6, and everything to the left. All right, so which values of x are represented in at least one of those pictures? Again, this is an OR problem, so we're just looking for x to be represented in either picture. Well, the answer is all values of x are in one or the other of those pictures, aren't they? If x is less than 0, then it's in the second picture. If x is between 0 and 6, it's in both pictures. If x is greater than 6, it's in the first picture. The numbers 0 and 6 are in both pictures. So every number, every real number is in at least one of those pictures. The solution set for this inequality, this compound inequality, is all real numbers. And I don't remember if it ever came up in chapter 2, how to write all real numbers using interval notation. You just write negative infinity, comma, infinity with parentheses at both ends, because you always put a parenthesis next to an infinity symbol. And that's going to take care of section 9.1. We'll see you next time.